It's a pleasure to have Leo Petrov coming from, well, from online, but I guess from UVA right now, to speak to us about symmetric functions from Vertex models. I think everyone's probably been to these talks before, but if you have questions, feel free to either unmute yourself and just ask Leo the question, or if it's a question which maybe is not as pressing or can be addressed by other people, feel free to just put it in the group chat. Just make sure to address it to everyone, because if you direct it only to Leo, he might not see it in the course of the talk. Anyway, well, Leo, why don't you take it away?
All right, thanks. So this is based on two of my works from this year. One is with Matteo, and the works are on pretty close topics, but they're unified by the presence of vertex models. So before I start, let me take a moment to express my solidarity with people of Belarus and their peaceful insistence on their vote for change. So if you haven't heard about what's happening, then I can tell you more, but it's kind of important to me and other people, I'm sure. All right. Anyway, so I'm going to show you this table of different families of symmetric functions, which all can be traced to vertex models, to integrable vertex models, including McDonald polynomials and everything that is obtained from McDonald by degeneration. And also, there are some other new families of symmetric functions that are discovered by looking at integrable vertex models. Today I'm going to talk about first in a simpler setting about spin-hole Littlewood functions and the determinant summation identity for them. And second, there really would be two parts, and there would be mostly independent. And then the second part is going to be about spin-Q-Whittaker and spin-Whittaker functions, and there are some connections to polymer models, which I'll touch at the very end. And there are more questions in the probabilistic setup. So mostly I'm going to talk about symmetric functions. So integrable vertex models mean that there is a commuting family of transform matrices usually. So in a more straightforward setting, transform matrices are linear operators from a tensor power of a finite or infinite dimensional space, let's say finite dimensional space, and their matrix elements are defined on bases on the standard basis of a tensor power by saying that, well, the matrix elements should have a specific product form, which is interpreted as a product of vertex weights, so that the whole product is a weight of a row of vertices. Here, my basis vectors mean that if I have E0 means that there are no arrows at the vertex, E1 means that there is one arrow at the vertex, and so on and so on, up to some E sub r minus 1, where r is the rank of the model, but also we can, or r plus 1 should be the rank. Okay, but also we can have infinitely many arrows arbitrary many arrows occupying in a slight generalization of this. Anyway, so graphically, each matrix element, each product of vertex weights, means that can be interpreted graphically as a weight of a configuration of paths at a single row of vertices, where you have A arrows entering from the left, like here A equal 1, and B arrows exiting from the right, like B equals 0 here, and A and B are fixed. And then I1 that IN are labels of the image, and J1, Jn labels of the result, like labels of the target space. And then we are by fixing I and J, we determine the configuration of arrows on this lattice, and then we assign a weight to this configuration by saying that the weight of a configuration is a product of individual vertex weights, Wx, where they're chained in the sense that K1 exits vertex number 1, then enters vertex number 2, and so on and so on. So if the model is integrable, this usually means that transfer matrices with different spectral parameters commute. So vertex weights might depend on spectral parameter X, and you'll see in examples how this dependence goes. But integrability usually means that transfer matrices with different spectral parameters commute. This, depending on A and B, you can link. You can take model and cylinder where you glue A and B together, and this is one way of doing it. And we are not doing cylinder. We are doing lattice, like finite lattice, and then later we immediately pass to infinite lattice, meaning that we have infinitely long rows of vertices. And anyway, depending on A and B, if A or B are equal to each other, then usually the transfer matrices simply commute. And however, if A and B are not equal to each other, then it might be that the transfer matrices satisfy a more complicated commutation relation or exchange relation, which is related to the Yang-Baxter equation. So here is an example of one of the relations in one of the models. And if you imagine layering many operators on top of each other, then you would see that this is going to be pretty messy if you use these relations repeatedly. So instead of doing this, which is done in many other works, we can also pass to infinite lattice and let capital N go to infinity, so that one of the terms in these relations actually dies out in the limit, and the Yang-Baxter equation reduces again to a kind of a commutation relation, which becomes much simpler. So if, in any case, if there is enough commutativity, then it means that we can exchange spectral parameters. And so by considering layered partition functions, we would get, with certain boundary conditions, we would get partition functions which are symmetric in the spectral parameters. And the goal is to study them is to link them to known symmetric functions from the symmetric functions theory, and also to get their properties from the exchange relations, from the Yang-Baxter equations. So in the first part, I'm going to discuss thin-Hall-Littlewood functions, which are the simplest example. And they were recognized by Borodin explicitly in explicit form and linked to Hall-Littlewood monomers, but there were many previous works discussing various aspects. And as an application of the Yang-Baxter equation, we will get a new determinant summation formula for these functions. So vertex weights are defined like this. So here you have a spectral parameter U, which enters formulas in many places, and then you have a parameter S, and then you have a quantum parameter Q, which is between 0 and 1, and then you layer the row operators on top of each other and impose certain boundary conditions, and in this way you obtain inhomogeneous spin-Hall-Littlewood functions, f lambda of u1 un, where lambda is the label of the top boundary condition, which can be arbitrary, and lambdas encode arrows exiting from the top, like lambda 1, like there is an arrow exiting at location lambda 1, at location lambda 2, at location lambda 3, and so on. And in this model we have, by the way, we are allowing arbitrary many vertical arrows per edge. And we also take inhomogeneous parameters here, and it's important for some things, or we can take inhomogeneous parameters. And this way we have another parameter psi, which we make dependent on the horizontal coordinate, and then u's are depending on the vertical coordinate, and then the parameter s also will depend on the horizontal coordinate. So here's an example of a weight we take. All right, so the weights satisfy Yang-Baxter equation, actually several instances of the Yang-Baxter equation. So let me give you an example. So this is kind of an exchange relation in the case capital N equal 1. So in the case our row operator is just a single vertex. These relations can be encoded by putting a cross vertex from the left and from the right. And the Yang-Baxter equation tells you that if you fix the boundary conditions, boundary numbers of vertices, i's and j's, and you sum over all k's inside, then the partition function of the configurations on the left is going to be equal to the partition function of the configurations on the right. So here is an example of a type of a Yang-Baxter equation. And here, the red vertices were defined on the previous slide. And there are two other types of vertices, the blue ones and the cross ones. And their weights are defined inside in similar ways. So they also depend on a kind of a spectral parameter. So capital R will be cross vertices, and they have a spectral parameter which is equal to the product of spectral parameters in the red and blue. And the blue weights are called dual weights, and their arrows go kind of to the left and up. And I'm not going to, well, I don't want to go into full detail here, but I would just say that everything adds up. These weights indeed satisfy the Yang-Baxter equation, which is easy to check. There are many cases, but you can use your favorite computer algebra system to check it automatically and get the equation. And the Yang-Baxter equation allows to prove many properties of the symmetric functions. So let me give you an example of a Cauchy identity where you take a product of two things. One is the F lambda I talked about. The other is G lambda star, which is a different symmetric functions involving blue vertices where you also slightly change boundary conditions. Namely, here I'm talking about taking taking no incoming arrows from the left or from the right, but also but all the arrows should exit from location 0, and then they enter from the bottom at coordinates lambda. So this is the G lambda star, and then you take F lambda and G lambda star, take these products, sum over all possible lambdas, and as a result, you get a very simple product formula. And to see why this is the case is kind of straightforward using the Yang-Baxter equation. So the idea of proof is just in these two pictures. So we consider two partition functions of multi-layered configurations, where here I have on the left there are multiple configurations. So I impose boundary conditions. So my boundary conditions here are going to be arrows incoming in the red part and then outgoing from the blue part, and nothing happens in the right boundary. And so the summation over lambda means basically that I do not specify anything else. And then if I cut this picture like this, then in the red part I would get the F lambda, and in the blue part I would get G lambda star, and so I have a product of them, and then I need to sum over all lambdas. Here the R weights on the right crosses are going to be all equal to 1, so there is no additional factor here. And then on the right, when we apply the Yang-Baxter equation, a total of n times m times, then the crosses would all move to the left. And if you recall the R weights, then you see that the boundary conditions like this. So the boundary conditions are fixing the arrows incoming here and outgoing here. And then if you look at the R weights, then there is only one configuration of the R weights that is possible in this region, in this rectangle. and the weights are equal to 1 minus q u times v over 1 minus u times v, which leads to the double product in the Cauchy identity. And then prefactor is just the partition function of this remaining red part here. So you get this prefactor. All right, so this is the Cauchy identity. Okay, so this is just a glimpse of spin-Hall functions. They satisfy many other nice properties, including explicit formulas, orthogonality relations, and others. They have different particular cases. So in particular, if you set S equal to 0, you get Hall-Littlewood symmetric polynomials, classically known. Or if you set S parameters and Q both to 0, you get even more classical Schur symmetric polynomials. And the Cauchy identity for them is very well known. There are about 5 proofs, and the Ambaxer equation proof is yet another proof of the same identity. In some other degeneration, let me just remark that you can also get interpolation Hall-Littlewood polynomials, which are Hall-Littlewood limits of interpolation McDonald polynomials. And I'm throwing it here because I haven't seen probability theory done with interpolation McDonald polynomials. And if you know about some ideas, I'd like to hear them. Tell me, please. So my main point is that one of the degenerations of the spin Hall-Littlewoods is the family of Eigen Functions of the asymmetric simple exclusion process, which is an important particle system in integrable probability, and I'll define it a little later. And to get this degeneration, you need to set S to be 1 over root Q and C equal 1. And in this case, the weights become 0 if you have more than 1 vertical arrows per edge, which means that everything specializes to having just 1 vertical arrow. And this implies that the function G lambda star doesn't make sense, because in G lambda star, one of the boundary conditions was a staggered, clustered boundary condition where you have all the arrows exiting through the same vertical edge. So in fact, you can use the Ambaxer equation to actually obtain a Cauchy-like identity, which makes perfect sense in the ASEP specialization. So this is what I'm going to explain next. This computation is slightly more involved, which you will see next. So here's the replacement for the G lambda star. So instead of G lambda star, I would like to use F lambda star, which is going to be very similar functions to F lambdas, where I'm taking blue vertices, W star, the dual vertex weights, and there is, so if in the ASEP limit, you would disallow things like this, where you have 2 arrows per edge, but that's okay because lambda would then just be strict collection of numbers, strict partition, which is fine, as long as I don't get this type of boundary conditions. So I don't want that. If you take sums of products of F lambda and F lambda star, you would get a much more complicated right-hand side, which is an explicit determinant, and this is the result. And besides putting F lambda times F lambda star, you can also introduce a refinement factor here, where gamma is any parameter, any non-zero parameter. And here you have Pohammer symbols with M naught of lambda, where M naught of lambda is the number of zeros in the lambda. So lambda has a bunch of zeros, maybe from 0 to n, and this is a refinement factor that keeps track of the number of zeros. And so when you sum this up and impose certain analytic conditions such that u times v is sufficiently small, then you get an explicit determinant. So this explicit determinant, this idea, this whole Yang-Baxter approach was already done in the Hollywood case by Wheeler and Zingerstein, and this theorem is obtained by somewhat repeating, by essentially repeating most of their argument, but there are some issues with computations that I don't want to go into. So the Hollywood case you get when you set S not equals 0 and something else. You can also do other things, like you can also set. So this identity is pretty nice in the sense that, well, it deals with symmetric functions. It has an explicit right-hand side. Right-hand side is, however, a determinant, which is quite complicated. And then you can specialize this determinant, this identity, in different ways. And there are many ways you can play with this identity. So one example is when you set gamma equal 1, you kill this refinement factor, and you get a Cauchy identity with a determinantal right-hand side. And in the right-hand side, something much simpler happens because in the determinant, this factor is removed, and then this factor is a product factor. So you get a determinant which has a special name. It's the Iserdin-Korepin determinant, and it appeared in 1980s in connection with integrable vertex models. Another form of the same determinant, you can also write down a very non-trivial identity between determinants, which I cannot prove. Well, I don't think there exists a proof of this by using matrix manipulation. So it doesn't seem to be true that you can take one matrix, multiply, divide by other matrices and get the other matrix. I don't think so, because the ratio of the two matrices is quite crazy. But there is a way to write one determinant in terms of the other determinant. So what's going on here is that here in the left hand side, this function is taking the form of like function of ui comma vj, and so because of this, you know that the determinant is anti-symmetric in the v's, so that you can divide it by the van der Waals determinant, and then the ratio is an explicit determinant where now inside you see that v's are entering in a completely symmetric way. So this is the only way. This is the only way where v's are entering is that they do this via the product. So this is some kind of a formula that I first learned from paper by Kuyenko on interpolation whole polynomials, but I'm sure these things have been done before in other contexts. Anyway, so how to prove this? Well, you use pictures. So the proof is again, well, the idea of proof is again in a single picture. So here, the right-hand side, you see the sum over lambda. So these are my boundary conditions. And then I'm introducing in the column number 0, I'm putting not 0 arrows, but some number a arrows, and then q to the a will be my refinement parameter gamma. So you can think a equals 0, then you get to the second identity, and then you add Yang-Baxter, Yang-Baxter crosses to the right, Yang-Baxter crosses to the right. You add them like this, and then you move them all the way to the left, and then you get to the left-hand side, and the result is going to be a partition function of a model of a picture where the boundary conditions actually make not just one non-zero, not just one non-trivial configuration, but the remaining non-trivial configurations. And because of this, we would need to compute the partition function on the left. So here is a reminder of my R sub z weights. And computing this partition function is done using Lagrange interpolation, which is essentially the same approach that was used by original works of Iserdin and Korepin on computing the partition function of a similar form in a determinantal way. So what does it mean, Lagrange interpolation? Well, basically, because you're dealing with the partition function, you have that it depends on the ui's, vj's in a polynomial way of a controlled degree. Well, after you clear up the denominators, there is a controlled degree. And then also the function is symmetric in the u's and v's. And then by setting u equal to maybe u equal to 1 over v, you would kill several of these weights, and then you would get a recurrence for the order n partition function to the order n minus 1 partition function. So this would lead you to a set of properties that uniquely identify the partition function, and then you take your scary determinant, and then you show that this scary determinant also satisfies the same properties. And how to come up with a scary determinant in the first place? Well, it's done by experimentation, by just saying, okay, n equal 3, what do I get? I can figure it out. I can figure out the determinant, and then this allows me to get the end formula. All right. So there is some connection to many other things. Namely, there is a connection to McDonald measure averages. So if I set s equals 0, then there is some reduction here, which goes from spin-Hall-Littlewood functions to so-called stable spin-Hall-Littlewood functions, and there is an identity which you can take. Well, remember that I'm dealing with the same scary determinant, just specializing it a little bit. And then the determinant I can also expand in the basis of Schur symmetric polynomials. And this expansion is very nice. So I'm taking the determinant as a function, as a symmetric function of u's, and then I expand it as a, because it's symmetric, so it should have a Taylor expansion in s lambda of u's. And the coefficients are surprisingly s lambda of v's times a very simple factor depending on lambda. And then I recognize from this Schur expansion, I recognize that this is an expectation of a certain quantity with respect to the Schur measure. And what I get is then we can also go to previous works, including work of Olli Warnar and from 2008, and based on even earlier works of Kirillov Naomi, which shows that the special expectation of, which basically deals with this identity between these two things. It tells me that the Schur measure expectation is the same as the McDonald measure expectation, where you set q equal, so to go from here to here, you set q equal t, and then going back is the tricky part. But it turns out that a certain McDonald expectation does not depend on one of the parameters. And then what we get is that this same thing is equal to a determinant, and then it's equal to this expectation with respect to the spin-Hall-Littlewood measure as well. Much more recent, recently it was recognized by Alexei Borodin that this same formula actually relates to stochastic 6-vertex model and the expectation of the height function. So there is some application. So basically, this, especially the Schur measure connection, gives much hope to asymptotic analysis of Iserdin-Kurepin determinant, because we know everything about Schur measures. Okay, so let's go to ASEP case. Let's discuss applications to ASEP. So ASEP is a continuous time stochastic particle system, continuous time Markov chain on particle configurations on Z, where there is at most one particle per site. Particles are allowed to jump left and right. They jump right with rate 1, jump right with rate q, jump left with rate 1. They do it in continuous time. And I assume that there are finitely many particles, basically k particles. And then using beta ansatz, one can write down eigenfunctions of the Markov generator of this of asset. So the Markov generator is basically collecting all the jumps in the form of a linear operator. And this linear operator has eigenfunctions, which are given by the following symmetrization formulas. And I forgot to write on the slides, but this is basically, if you take f lambda and then you set s equal to 1 over root q, then essentially this is going to be this thing. So essentially f lambda is going to be equal to this guy, where lambda is replaced to x, is replaced by x, and there is no s, so there is a q here. So if you take limit of the spin-Hall functions, you get asset eigenfunctions. So Tracy and Widom used these functions and orthogonality of them to write down. Well, this was just the first step of solving the asset. But the first step is to write down explicitly the transition probability in ASEP during time t from configuration X to configuration Y. And this transition probability is given by multiple contour integral, where here inside the integral you have a product of two eigenfunctions, and then there is an exponent of the eigenvalue. So this is basically classical Fourier analysis. Once you know the diagonal, once you diagonalize the operator, you can then find the exponent of the generator. So basically, this is the operator, which is the exponent of the exponent of the Markov generator is going to be the transition function. All right. So then they use properties of the eigenfunctions to get from multi-point observables, like transition function involves multiple points x, multiple points y. So they use various properties of the functions to get to single point observables, and then they do asymptotic analysis. So one of the formulas is the summation identity for eigenfunctions, where you take one of the p's, is sum over all possible x and y, over all possible x's, and then you get an explicit product formula. This is one of the magic identities. I'm sure this identity can be traced to Littlewood identity for spin-Hall functions, which exists, but I haven't written down. So from the spin-Hall Littlewood business, we get a determinantal identity, where you take a product of two eigenfunctions, left and right eigenfunctions, and sum over all x's, and then you get a determinant. And this observation was made by Ivan and Zhiping Liu in an unpublished work, and then Zhiping told me about this, and then I said, well, it should come from spin-Hall Littlewood business, and indeed it does, and so I got this generalization. Yeah, so using this second identity, there is some access to multi-time formulas for ASEP. So I'm just going to give you a very simple formula, because even with this formula, I don't know what to do asymptotically. So we can just take a two-time formula. So we take 2 times T1, T2, and then we ask for the probability that the first particle at T1 is to the right of some number, and then the first particle at T2 is to the right of some other number. And using Markov property, this is just going to be a summation over x1, x2 of products of two transition functions. So if you write them in the integral form, you would get integral where you have 4 eigenfunctions, and in these 4 eigenfunctions, you can use the summation. Can use the summation to sum over. Can use this second determinal summation to sum in between, and so this collapses the formula somewhat. Well, there are no sums at least. So in the end, you get the following formula, which does not involve any summations. So I forgot to say, here in this formula, you also need to start from the step initial configuration. So here here you need to start from densely packed, configuration. Yeah. There are k particles in total, so I don't even take infinitely many particles, but you start from the densely packed configuration, and what you get is a big integral which involves double the number of variables, and there is still one eigenfunction inside, but that's less of a problem. So I don't know how to do asymptotics with this, but it should be somewhat accessible. So it should give you some control of multi-time asset distributions. Of course, there are many obstacles before you can start asymptotic analysis. So asymptotic analysis has been done in many models. Of course, beyond determinantal, it's much more complicated. In the ASEP single time, single space, it was done by Tracy Widom. For the 6 vertex model, the 2-point analysis was done. What is the number of? Okay, so there is a question: what is the number of eigenfunction? I'm just saying how many eigenfunctions would be in your formulas. So eigenfunctions. X denotes space coordinate, Z denotes spectral thing, which we're integrating over. Okay, anyway, so in the determinantal case, there is a big distinction between space-like and time-like paths along which you study asymptotics, and there are some good results. Best results are available on a ring instead of a line, and I don't understand why, but there is some nice property of the ring, which allows this, but there are some multi-time. Okay, I'll probably answer this question. Okay, I didn't. Right. So Sergey, I don't think I understand the questions you're putting in chat, but I'm going to the second part now. So I can answer this question. How many eigenfunctions? Well, if you're asking how many eigenfunctions, then of course our space is infinite. So there are infinitely many eigenfunctions. They are indexed by a continuum, continuous parameter z, which belongs to c to the k, where k is the number of particles. And it means that in the Fourier analysis, instead of summing, we need to take contour integrals. And that's what we are doing when we talk about orthogonality of eigenfunctions. All right, so let me all right, so I'm going to start with another class of functions, and I can answer some other questions if you have them.
Leo, I think with the question about the number of eigenfunctions, maybe the confusion is that we're not in a finite dimensional setting, right? We're not dealing on a finite lattice with boundary conditions. So there's an infinite number of eigenfunctions, right?
Right, and they're indexed by continuous parameters. So in the inverse Fourier transform, you need to take integrals instead of sums. So I hope this answers Sergey's question. Okay, so let me go further and discuss another family of functions. So there will be lots of formulas. So you shouldn't. I'm not assuming that you understand these formulas right away. So I'm going to use again 3 types of vertices: the blue and the red and the cross vertices. And basically, if you take spin-hole Littlewood vertices and you take some procedure called fusion, which involves certain layering of vertices and then summing up and then specializing, then you preserve this fusion preserves the Yang-Baxter equation. So the fusion is a nice procedure preserving integrability of the models. And after a number of steps, you arrive at other types of vertices, which is also nice. And this would lead to spin Q-Whittaker symmetric polynomials. So these are some types of vertices, and the weights are given by product formulas. And there are some kind of boundaries in the whole picture. So in the second setting that I'm discussing, I'm going to involve left boundary and the right boundary of the model, and this will make life much easier. So the vertices, the red and the blue vertices are okay. They have product formulas with cupohammers, and then the cross vertex is much more complicated. It doesn't have a product form. It has a form which is involving Q hypergeometric function 4, 5, 3. Also, these weights probably should be expressible through Q-Raka orthogonal polynomials in single variable if you match the parameters. So these weights satisfy the M-Baxter equation. So let me.
Sorry.
Yeah.
On the slide you just did, you said that the spin-Q-Whittaker weights are a fusion of spin-Hall-Littlewood ones. So the spin-Hall-Littlewood ones, you've already performed fusion so that you have infinitely many particles allowed to go in both directions. How do you perform fusion again?
Right. So thank you for the question. So here I'm allowing, right. So in the spin-Hall-Littlewood case, I'm allowing at most one particle going in the horizontal direction, at most one arrow going in the horizontal direction.
Oh, so you've only fused vertically so far?
Here, yeah. And then from spin-Hall-Littlewood to spin-Q-Whittaker, I'm fusing horizontally by allowing ij numbers to be arbitrary, non-negative integers, like you see. These are cupohammers. Okay. So so I'm going to I'm going to briefly define. So we are doing the same things. I'm going to briefly define spin-Q-Whittaker functions, or in fact they're polynomials because the weights are polynomials. Well, except the cross. So this f lambda is the spin-Q-Whittaker function, and then f star is the dual function, and they're defined as partition functions of layered row operators, of layered row configurations. So it's basically the same thing. Here lambda plays a slightly different role. Dual role, actually lambda prime plays the same role. There are reasons for this notation, but anyway, so I'm just going to kind of run through spin-Q-Whittaker and then get to spin-Whittaker limit, which has connections with random polymers, instead of spending time repeating the same stuff about spin-Q-Whittakers. So so the spin-Q-Whittaker polynomials. So what this quantity is actually an element of the transfer matrix capital T from the very first slide that I was discussing. So it involves lambda i's. Whoa. Yeah. Okay. So it involves lambda i's and mu i's. These are going to be index of the multi-vertex configuration from below and from above. All right. So I'm going to comment on this connection, on this discrepancy between spin-Q-Whittaker, what I'm talking about, and the original spin-Q-Whittaker polynomials introduced by Borden and Wheeler in 2017. So there is a simple relation. So Borden-Wheeler version is related by a simple factor, depending on x, to our functions. And it turns out that this, sorry, I think my, do you see everything fine? Was it blinking?
A blue square with Borden-Wheeler's version and two formulas in it.
Yep. Yep. Okay. So right, it was blinking, so I don't like it, but okay. Anyway, so I'm going to So it turns out that our functions actually reduce to Borden-Wheeler by just setting one of the variables to 0, and we come up with these functions. Turns out our functions with Matteo, they have much nicer properties, but how we came up with them? Well, we basically were typing up Borden-Wheeler's functions in Mathematica, and we wrote the product up to k instead of the product up to k plus 1 in the star formula. And surprisingly, after you take layered sums of these, you get symmetric functions. And this is how we discovered them. And then we came up with Young-Baxter model for these new functions. And it turns out that these are somewhat nicer. All right. So the Young-Baxter equation here, the situation illustrates that we are allowing more than one horizontal arrow, so it's kind of more interesting and more complicated. It's not so easy to check, but again, we don't need to check the Spin-Q-Whittaker equations because we can just deduce them by fusion. So there is a Cauchy identity. There is a bunch of Q difference operators. So I'm going to repeat everything in the Spin-Whittaker case. So let me talk about the limit. So right, classically Spin-Q-Whittaker, classically Q-Whittaker polynomials, which are t equals 0 limits of Macdonald polynomials, the Q-Whittaker polynomials are interpreted as Q deformations of the GLN Whittaker functions. And there's been a number of works, including Gerasimov, Lebedev, Oblezin, and other people in various combinations in the 2000s, where they prove many properties of the Q-deformed Whittaker functions. And the Q-deformed, as Q goes to 1, Q-Whittaker functions turn into Whittaker functions. Whittaker functions are specific matrix elements in representations of GLN, and they have other nice properties, and turns out that Q-Whittaker functions can be, well, properties of Whittaker functions can mostly be obtained from the Q-Whittaker setting. And then it also turns out that our spin Q-Whittaker functions, which have an extra parameter, they also have a nice Q goes to 1 limit, and these new functions we call spin-Whittaker. Our spin-Whittaker functions are not representation theoretic yet, but they just have some nice properties. So limit transition is the following: we need Q going to 1, and then we rescale everything. We rescale the variables, we rescale the lambdas, we rescale the parameter s, and then we get a non-trivial limit. This limit depends on real xi's, real li's, and the real parameter capital S. As little s equals 0 corresponds to capital S going to infinity. So as capital S goes to infinity, we actually get the usual Whittaker functions, of usual GLN Whittaker functions. So it's a conjecture because we were not dealing with decay estimates. We just took formal limits of integrands, and it might not be that integrals converge to integrals, but we believe they are. So anyway, so our spin Whittakers should reduce to classical Whittaker functions psi, and so here's the definition of classical Whittaker functions, which I'll just flip over. So the spin Whittaker functions admit basically similar properties to the Whittaker functions. Namely, they have a integral representation over. They have integral representations over interlacing arrays, and this is a remnant of the definition of the functions. The definitions of the functions according to vertex models. Here is a couple of examples. So we basically have so these are symmetric functions which are supposed to be nice, and if you look at them at just a couple of first examples, they are nice, but they're kind of very general. So the second function for n equal 2 is basically the generic, well, yeah, it has 3 parameters. So it's basically a generic Gauss hypergeometric function 2f1 with 3 parameters, and we encode them so that they're symmetric in x and y, and then these functions they satisfy a number of nice properties like Cauchy integral identities, which replace the Cauchy summation identities. Also some connections to probability, also eigenoperators. So yeah, so there is, well, basically, let me just list a bunch of properties. So there is a Cauchy identity where you integrate spin-Whittaker times another like G spin-Whittaker function, and then you get a product formula. So it's a Cauchy identity. Also, you get that acting in the x variables, these spin-Whittaker functions satisfy well, they're eigenfunctions of certain difference operators. Well, there were Q difference operators at the Q level, but now there are difference operators. Also, it's known that Whittaker functions, actually for arbitrary Lie type, but especially in the GLN situation, Whittaker functions are eigenfunctions of the quantum Toda Hamiltonian, which is a second order differential operator. And here you have so here's the usual Toda operator, and here you have these exponents of ui plus 1 minus ui, which are just positive roots. And our spin-Whittaker functions, they admit a 1-parameter deformation here, and it seems that here I'm getting, you know, all. Sorry, these are primitive roots for the quantum Toda, and the deformed quantum Toda involves all positive roots. So, and then what we have is that our functions they satisfy in after a slight change of variables, they satisfy a eigenrelation with the quantum Toda Hamiltonian acting on the u variables, not on the x index. As every family of nice symmetric functions, there should be orthogonality. Well, one orthogonality is kind of given by this Cauchy identity, but there is another orthogonality which involves integration with respect to the variables, and it's known that Whittaker functions are orthogonal with respect to integrals, including the Skladin measure. Skladin measure Skladin measure contains only like 1 over gamma of z minus z, and our deformation of the Skladin measure would involve 4 gamma factors, and we hope that there is an orthogonality of the spin-Whittaker functions. However, we have no idea how to prove it because we don't have representation theory for the spin-Whittakers. Right, so the last thing I would like to talk about in the last 5 to 10 minutes, maybe 5, is that, well, spin-Whittaker functions, and Q-Whittaker as well, but spin-Whittaker functions are connected to random polymer models. So this connection is in line with the general scheme of things where you have symmetric functions satisfying Cauchy identities. Then you use this Cauchy identity as a normalization identity for a probability distribution on lambdas. And for example, for sure measures, you would get the probability of lambda is proportional to, you know, S lambda of x times S lambda of y. And the z, as you sum over lambda, the z gives you, the z is given by a product thanks to the Cauchy identity. So when you have a Cauchy identity, you would want to consider a measure which corresponds to this identity. So here, spin-Whittaker functions can also be made positive by certain choices of parameters, and we can then define spin-Whittaker measures and spin-Whittaker processes. Like this formula is basically the same as in the case of Schur processes or McDonald processes, where instead of taking just measure on a single lambda, you take a suitably coupled distribution of several lambda i's, of several lambdas. So here my measure lives on L double underscore, which is the interlacing array of reals. So anyway, there is some, basically, bottom line is that there is some probability measure based on spin-Whittaker functions, and we connect measure to particle systems, to integrable particle systems. Well, in this case, there would be integrable polymer models. So if I take my interlacing array like this, then left hand side of the array, left diagonal of the array, is related to the so-called streaked weak beta polymer, and then the right side of the array has another polymer interpretation, which is called weird beta polymer, which we don't have a good model for, and it's related to a limit of Kuchan-Pushtasov, which is another particle system. So so there are two polymer models. One is a simpler polymer model, which I'll discuss, and then there is a weird polymer model, which I'll show you in the next slide. And so however, the weird polymer model is also nice in a limit to the classical Whittaker case, where S goes to infinity. So there is the spin Whittaker, and then there is a Whittaker level below it. And so in the Whittaker level, the weird polymer model goes to log gamma polymer, which was introduced by Timo Seppalainen and polymer model. A streaked weak beta polymer goes to streaked weak log gamma polymer, you can say. And it's also a nice polymer model. So at the Whittaker level, these two models are very close, very similar, but at the spin level, they have one of them is much worse than the other. So the streaked weak beta polymer is a randomized, well, it's a random polymer model. So you take environment, where in your environment you take beta weights. So these are beta distributed random variables which are independent. So Bij are independent, and then using every B, you weight the horizontal edges by B and diagonal edges by 1 minus B. So horizontal and diagonal are dependent, but otherwise everything is independent. And then Z is going to be the partition function of all paths going from left boundary to your point. So it's going to be the strict weak beta polymer, and because it's partition function, satisfies a random recurrence. And this model was introduced by Ivan Corwin and Guillaume Barakan 5 years ago. And it's been solved, and there are some asymptotics you can do using counterintuitive formulas. And so here's the weird polymer model, and well, it's a random recursion. So let me walk you through this. So it's a randomized recursion here, Z tilde, where the recursion now depends on the ordering of the two previous values. So either Z tilde at one place is bigger than the other or less, and the recursion weights W, they involve certain distributions, and the distribution weights are based on, well, you can explain what, so NBB is negative beta binomial distribution, where you can explain what it means from classical probability. Basically, you take a P which is beta distributed on 0 and 1, and then you take so beta distribution on 0, 1, you take P as a prior, and then you sample with this P, you sample an integer. Sorry, it's not an integer. So yeah, so you use it to sample a negative binomial distribution. Then you do something else to get a density on 0, 1. and the density explicitly is given in terms of 2f1. So it's a weird polymer, but cool thing is that as capital S goes to infinity, this polymer model simplifies and becomes essentially like the street weak beta polymer, but with weights on the square lattice, and independent weights at sites instead of edges like in the street weak case. All right, so this is the last slide. So my talk had two parts. One is that, well, the main point is that symmetric functions are interesting and continue to be interesting and useful in integrable models. And symmetric functions that we know of, they all can be traced to integrable vertex models. Well, especially those I showed you in the first place. There are other classes, but I'm sure all families of symmetric functions should be traceable to integrable vertex models. Symmetric functions correspond to SL2. Non-symmetric versions of them would correspond to colored or SLN vertex models, or higher rank and other types. In the first part, I discussed the summation identity leading to Isергin-Korepin type determinants, and connected it to various other things like expectations with respect to McDonald measures. And this leads to, well, this gives some handle, at least at the level of formulas, for multi-time asset distributions. Yet I don't know how to do asymptotics. So in the second part, I discussed spin-Whittaker hierarchy. So there is like a new part of families of symmetric functions, and spin-Whittaker functions satisfy nice properties. However, a big issue is orthogonality. We don't know how to do it, and there are, from the connections to random polymers, we can ask, since at the Whittaker level, we know that Whittaker functions are intimately related to random polymers. This relation can be realized using so-called geometric RSK correspondence. And this was done by Corbin O'Connell, Seppeline, and Zigoras. And right, so this was done like 10 years ago. And this involved, understanding polymer models and then understanding multi-layer polymer models. So with the presence of new spin-Whittaker processes, there are multi-layer distributions, but I don't know of a polymer realization of them. And this seems hard enough because, multi-layer realization should encompass both polymer models on the same footing. And well, they both are involved with, they both depend on, beta random variables, but other than that, they're pretty different to me. So far, so it would be a very nice project to find geometric RSK for beta polymers and some other things. Like, also, it would be nice to find representation theory for spin-Whittaker functions, which might help proving orthogonality. All right, thank you very much. Sorry for going slightly over time.
Well, thank you very much, Leo. Well, we do still, if people have questions, we can take a few more minutes. Otherwise, you can discuss with Leo offline. Just feel free to either post in the chat or unmute yourself. Leo, you mentioned about using these connections with Schur for taking asymptotics of the Integrable. Are there kind of, I know this is kind of floated around at various times, but are there instances of this being done, being useful? And
I don't know. Well, it seems that at the area level, that's what you guys are doing with KPZ and area, and so it's kind of same ballpark, but I don't know if it's been done. Yeah, I'm not considering it.
Yeah, we certainly use that type of connection between the vertex models and Schur measure, but I guess to actually just analyze the Eigen and derive some information about the symmetric vertex model.
No, I just said it. I don't know. I didn't even Google about like what are the asymptotics of visible incorrect determinants. Well, there are multiple parameters. That's the problem. So if you set them all to 1, then there is this 6/30 partition function, and there is asymptotics. But yeah. Okay. There's no questions. I was too fast probably, but still, people can go back and watch or look at slides. So let me post the link to slides again, just in case.
And I'll copy that into my. I'll post it on the website.
Okay.
Hey, well, anyway, let's all thank Leo for a very nice talk.
Okay.
And we will have another talk next week. And I'm trying to remember who's speaking. Let's see.
It would be Amol.
It will be Amol and Li Cheng. So Li Cheng will speak at 1 p.m. Eastern time, and Amol will speak immediately after at 2 p.m. So, and Amol and Li Cheng, if you're on, send me your abstracts and titles. So, okay, I'll see you all later.
See ya.